All right, so let's work through a distributed load type resultant here. So what I have here is just a little bit of an exercise in designing a hinge for a dam. So I'm on page 342 is where I'm at. So when you put a dam in like that, you gotta, you start backing the water up. You need somewhere for the water to go. I mean, there's obviously a river up there at the head of that reservoir, and it's putting water into the reservoir, so you got to let the water out. And that's done through what's called a spillway. So a spillway is just a way to let the water over the dam in a controlled way so it doesn't do any damage to the dam. I mean, you don't want just water running over the top. That's going to be problems there. So you come up with an organized way to get that, designed way to get the water around or through, or however you do it. There's many ways to design a spillway. Now, so we're going to try and figure out how to set the spring on top of this door. So we got a spring-loaded door, and we want that door to open when the water hits 6 meters high. And that way it'll let water out, and when the water goes below 6 meters, it'll close. Okay, so that the intent of this thing is to hold the water at 6 meters. And it should open as the water hits that 6 meter height. So to do this, we're going to look at the distributed load that happens when the water's 6 meters high. What we're going to have on top of that is a spring, kind of like the spring on a mouse trap or a rat trap like that, that's kind of turning the door. And the spring is going to resist the turning of the door. So the door just won't swing open. It'll swing open when the pressure is at a certain level. Similarly, you've got a spring on your garage door that does something like that, okay? A little different action there, but it's the same idea. As I was mentioning, those things are dangerous to work on, so always be careful of those things if you're ever around them. They got quite a lot of torque in them is the issue. All right, so we're going to go through two things here. First, we're going to get from this diagram of the dam with the swinging door that's spring-loaded on the top. And we're going to break that down to a distributed load that we can handle. And then once we're there, we're going to handle the distributed load and analyze it. So we're going to do two steps here. So the first thing is kind of that practical sort of thing that you need to do if you're working on a project like this. So the way you break this down is you start with the unit weight of the water, sometimes called the specific weight, and that's 9,807 newtons per cubic meter. So that's what water weighs. Now we're going to walk that on down to get it to this condition here. That's our intent, okay? So the first thing to do is to take the weight of the water, and water has a bunch of molecules in it floating around, obviously, and as gravity pushes down on them, they exert pressures in all different directions. Think about like a stack of marbles. If you push down on the marbles, they'll kick out sideways too, and that's what happens with fluid pressure and air pressure and things like that. So the way you get from the weight of the water, the specific weight, to the pressure exerted is you multiply the specific weight by the depth. So the specific weight of the water, we know it's 9,807 newtons per cubic meter. If we multiply that by the depth of the top, which is 4.8 meters, and then again by the depth of the bottom of that gate, which is 6 meters, we'll come up with the pressure. So at the top of that gate, we got 47,074 newtons per square meter. On the bottom, we got 58,842 newtons per square meter. So that's the force that would be exerted horizontally on a square meter of area. That's what that represents. And the deeper you go, the more pressure you builds up because you're deriving that by multiplying by the depth. Okay? So that's the force per square meter at the top and bottom of the gate. That's kind of like an instantaneous pressure, you might think of it, because it changes as you move further and further down. Now our gate is 2 meters wide, so if we take that pressure and multiply it by the width of the gate, we kind of take the width out of that pressure and turn it into a force per unit length. So if I multiply both of those numbers by 2 meters, I'll get to the instantaneous load per unit depth. Load is another word for force. So when I convert that into kilonewtons per meter, I get at the top of at point A there at the top of the gate, I get 94.1 kilonewtons per meter. At the bottom, I get 117.7 kilonewtons per meter. Okay. So we're doing all right with that, getting down there? Okay, that's where we got last time, okay? Yeah.
A specific weight is always going to be given to us.
Yeah, you'd have to know it for the fluid you're working with.
Okay.
Commonly, it's water in a situation like this. So yeah, it would have to be a given. Okay. All right. All right, now, what we're going to do now is find the force associated with that diagram. Now, and we're going to apply it at the centroid of the diagram. Now, we went over centroids. The centroid of a rectangle is in the middle, okay? And the centroid of a right triangle is at what I call maybe the third point or something like that. So in a rectangle, it's in the middle. At a triangle, it's at a third of the base from the right angle. So that would be right there, okay? See, I don't know where the centroid of a trapezoid's at, so that's why I'm doing this. I'm going to break it into two pieces. So that rectangle there has a value of 94.1 kilonewtons per meter. To find that base of the triangle, I take the total, the 117.7, subtract off the 94.1, and I get 23.6. Okay. So what I have there is a rectangle with a force directed at its centroid, and then I've got a separate triangle with a force directed at its centroid. So that's what I'm working with. Okay. So I'll go ahead then and find the areas of those diagrams, because that's how I find the forces. Okay. So I'm going to find the area of the rectangle and then the area of the triangle. Okay. So I got the 94.1, which is the value right here. That's how I get the area. That's how I get the dimensions on the rectangle there. And what's left over is what goes into the triangle. That's the idea. So what I'm going to do then is find the area of these load diagrams. I've got the 94.1, that acts over the 1.2 meters. The 1.2 meters I've kind of written over. It's that dimension right there. That'll get me the area of that rectangular diagram. It's 112.9. And measured from A, that'll be half the 1.2 down from A. That brain doesn't really work too well, does it? So what do we got there? We got 94.1 kilonewtons per meter times 1.2 meters. That's 112.9 kilonewtons at 0.6 meters from A. And the way I'm getting that 1.2 is I'm taking the 1.2 meter, right there. I'm taking half of it because I got a rectangle. So that's where the 0.6 comes from. So that's the load that rectangular diagram exerts on the door. It's right here. It's 112.9 kilonewtons. Okay, I also have the triangle. 1/2 times 23.6 kilonewtons per meter times 1.2 meters. It's 14.1 kilonewtons. And from A, that's going to be at 0.8 meters. It's from A. If I could spell from there. There we go, from A. And now the way I'm getting that is I'm coming down from the vertex. Okay, so I'd go a third of the height there from the right angle to the centroid, but to get to the centroid from the vertex, that's going to be 2/3 of the height, okay? So I'm going to take 2/3 times whatever that is, 1.2 meters, and that's going to get me 0.8 meters, and that's where that's coming from. So now what I've got is one load for each of the two diagrams, the rectangle and the triangle, and I've got their distance from A. Okay. So now I can figure out both the force they exert at A and the moment they exert about A, which is what I want to know. Because that way I can design the door and the spring. Okay. Yeah, question there.
Why exactly are you doing 2/3 height on
Okay, what's going on there is the magnitude of that load, which is what this diagram represents, is the area of it. But also there's a location where it's exerted. So I'm taking that spread out distributed load and putting it at a specific point, and the point where I put it is the centroid of the shape. So that's where the centroid is at. Okay, and that's why that's where those values come from. Other questions on that?
So splitting it in half, splitting it again.
Yeah, the rectangle is pretty easy. It's in half, but for a triangle, it's a third from the base, from the right angle. Yeah, that was given. That was on Wednesday. I went over that, but yeah, that's the standard centroid for a right triangle. So, and that's just a given. So if you took a cutout of a right triangle and found the balance point of it, it would be h over 3 from the right angle and b over 3 from the right angle. The balance point would be the centroid, okay? That's just a characteristic of a right triangle, property of a right triangle, okay? All right, we're good? So now to design this, what we want to know is, what's the net force on the gate? Well, the net force on the gate is the sum of the two forces. It's 112.9 plus 14.1, the force of the rectangle and the force of the triangle. So that comes out to be 127 kilonewtons. That's how hard the water pushes on that gate. So that's going to be part of your design, is making the gate strong enough to withstand that. Okay. Questions on that? Okay. So the last thing to do there is define the moment about the gate. So the spring setting is going to be that calculation on the top. It's the moment about A. It's the 112.9 times that 0.6 meter distance, plus the 14.1 times the 0.8 meter distance. Now that is clockwise. But, and what I have on there, if you look on top of that MA, is I show a clockwise arrow with a plus sign. That means I'm calling clockwise positive, okay? So I get to be emperor of this piece of work, and I can call clockwise positive if I want. So that's what I decided to do, okay? And see, the reason is it's just coming around clockwise. I don't want to put a bunch of negatives on there. Someone's asking me what's the moment. I'm going to tell them it is 79.1 kilonewton meters. It's actually negative, but I don't want to, I'm just going to tell somebody it's coming around this way, and it's 79.1. Those sign conventions are somewhat arbitrary. You got to hold to them once you pick one, but the right-hand rule, I think, was chosen primarily because most people in the world are right-handed. Okay? If most people were lefties, we'd probably have a left-hand rule. Is probably what we have. So it's arbitrary. Okay. So what I'm saying there is the moment is 79.1 kilonewton meters clockwise. Okay with that? So when I get down to designing that gate, that's what I'm going to design it for, right there. There's the sketch. A force of 127 kilonewtons and a moment of 79.1 kilonewton meters. If I want to get a little fancier about it, what I can do is take the moment and divide out the force, and that will get me an offset distance. So there's another way to look at it. There's the moment about A caused by the force. But that's kind of the bottom line there when I design that thing, or part of it anyway, when I design that hinge. Those are the factors I'm going to be looking at. So I'll set that spring on the hinge such that it will open when there's a moment of 79.1 kilonewton meters. Okay. Okay, we good to go on that? So that's kind of a breakdown of a distributed load, first in generating it, how to make that diagram, and then once we got it, how you can analyze it to solve a little bit of a problem there, okay? Good. Okay. All right. Let's look at one other little thing here. Okay. There we go. These are those little, if you've been out in the courtyard, there's benches out there. Let's say you're in charge of designing the bolts, okay? And somebody was in charge of that, okay? That's one thing you learn when you start doing design work is every little detail on every little thing, somebody had to think about it and figure out how to do it. So somebody had to figure out and say, I'm going to use 4 bolts and they're going to be this diameter and they're going to be this strength of bolt and they're going to be embedded this far into that concrete. Someone had to actually think all those details through, okay? And when you do design work, it's very detail oriented. You got to think about everything, okay? And you had to think about, can somebody get a wrench on those bolts or the way that's welded in there, and all these things. Yeah. Question?
Do you know if something like that they would pour the concrete and then drill and set bolts, or set bolts?
My guess is they drilled that because now if it's a serious bolt, like a serious structural bolt,
Yeah.
like what they hold columns up with, those are cast into the concrete. Something that's small, that looks kind of. I doubt they were messing with it, especially the Yeah, I mean, it'd be pretty tough to get those aligned just right when someone's out there pouring concrete. Ideally, you would pour around it, but my guess is you're right. They probably just drilled it. Okay. All right. So there you go. All right. So let's design this. Okay. So let's find the resultant at the bolts, so we can design the bolts. Okay. We need a safety factor on that. Yeah, that one had somebody jumping on that bench. I think I don't know when that happened, but I think somebody was jumping on that bench. Okay, now this is something when you're working, man. You got to go. Well, how do I handle that? I don't know. You need to find the dynamic load of somebody jumping on the bench. I mean, maybe you just double the size and call it good. I don't know. You got to come up with some way of dealing with that, though. Okay. Yeah. Okay. All right, so this is a little sloppy, and I apologize for that, but let's just walk through this. So I'm going to figure out so are you going to figure out that on this bench, are you going to design it for ballet dancers or sumo wrestlers? What do you think?
Sumo.
Yeah, right. You want to design it for the largest people you could think being on that bench, right? And you're going to
How much can you afford?
What's that?
How much can you afford?
Yeah, right. That's a good question, isn't it? Because it's money too, all right? But I'm going to take 300-pound people, and where am I going to put them on the bench? Oh, what page? I'm going to put them on the end, because that's going to cause more moment about those bolts.
Okay.
That's why I'm going to do that. And actually, this is on page 415. I'm sorry about that. I should have told you that. It's a little different, though. Scratch out the word reaction and find resultant. We're changing it slightly. So page 415, and change the word reaction to resultant. Okay, so I'm going to put 300-pound people at the end of the bench. I've got the dimensions on the bench. Now, the bench is made out of aluminum, I think. Now, when you look at that, it's kind of a mesh. Now, I don't want to spend all day doing that, so I said I got 50% voids on that, meaning 50% empty space. So I'm assuming I got 50% aluminum in there, okay? Because there's holes in the bench. So I'm going to take the dimensions of the bench, the 0.26, which is the length coming out from the wall there, times 1.8, times 0.05, because it's 5 centimeters thick. Then I've got the unit weight of aluminum, 28 kilonewtons per cubic meter, and 0.5. All right, and that's going to get me the weight of the bench, which is 328 newtons. Now, I also got 900 pounds on that bench, so notice the weight of the bench really, I don't know, it ain't much, okay, compared to the weight of the people. So I'm going to assume that load is 300 pounds times 3, 900 pounds. Now, I don't think too well in newtons, so notice I've got some units to fix here, don't I? So I've got, the load there is 900 pounds. I'm going to put a safety factor of 2 on this. Okay? So I'm gonna double the weight. I'm gonna get 1,800 pounds. So that's, yeah, question?
So like in an elevator, when it says it's designed to carry, I don't know if they put it in kilograms or
15
pounds.
people or whatever.
Yeah, is that with like pre-safety factor?
Oh, yeah,
Okay.
see, like these bolts, if one of
They
these
don't
bolts breaks,
trust us, dude.
Yeah.
I'm not gonna get too worked up, over, it wouldn't be good, but an elevator, yeah, those things, I don't know how over designed they are, but, I would be surprised if it's only a safety factor of 2 on those things,
No, because you use it to like transport things.
Yeah, and they're rated for a weight, but I bet you could get probably 2 or 3 or 4 or 5 times the amount of weight that they're rated for. That they're designed for that. Something that's that high a liability thing, it's gotta be way over designed.
Get some sumo wrestlers?
Load it up with concrete.
Yeah, that's probably the heaviest thing I can
Load it
think.
up with bags of concrete.
All right, so I'm gonna take that 1,800 pounds and I'm gonna add this, and I'm gonna come up with, that's just about 8,000 newtons. Because I gotta get into metrics, okay? I think in weight, because I'm from America and all that, and I think in pounds, I don't really know how many newtons 300 pounds is and all that. So I just converted that roughly into 8,000 newtons, okay? So that's my design load. That's, okay. Y'all okay with that? I'm getting a little rough here with the numbers, okay? I'm not doing real precise here on this one.
Wait, so load is 3.3?
Did you just do
Oh, I
newtons?
Yeah, see, what's up? I think in pounds, and I think of a really large, like a really large person, 300 pounds. 3 of them would be 900 pounds. I'm gonna double it to 1,800 pounds. But see, I've got everything in metric units here. I gotta get that into newtons. So I just converted it. And I'm being kind of loose on my precision on this, okay?
Where's your 28 kilonewtons per meter cubed? That's your.
That's a given. I looked it up in a book. That's aluminum.
Oh, is that the density of aluminum?
Well,
No, it's a
no.
specific weight. Density of a kilogram.
Okay, thank you.
I see what you're saying.
No, like the weight of the bench is not, okay.
We're good?
Yeah.
We doing all right? Everybody okay?
Why does
The weight-
multiplying
there's no way the weight-
items, why does multiplying an item's specific weight times its area,
It's volume. I've got 3 dimensions in
volume
there.
give you its?
Well, specific weight is weight per unit volume. You multiply that by volume to get the actual weight.
Okay.
Okay.
The 50% voids on the bench is the 0.5 you add that.
Yeah, right, because it's got holes in it.
Oh.
I got the units from.
We good?
Yep.
All right. We doing all right? Okay. Now I'm gonna draw a picture of the bench. Okay, there you go. And what I'm gonna do, I've got the 8,000 newtons on the end, that's the people, then I got the weight of the bench at B, and I've got the moment arms there. So I'm gonna take a moment, I'm gonna get the net force, and I'm sorry, that green just isn't working. And the time isn't working either. We'll finish this on Monday. I'm just not gonna get through this, so we'll get through it on Monday. Let's see, so let me give you a couple of these for Friday, okay? So remember our test is Wednesday, so these will be due on Friday. I'll find a couple of these distributed load ones to do. 241 and 242, those will be due on Friday. And we'll go over this, we'll do this again on Monday, I think. So 241 and 242 due Friday. And Friday is at the 7th, I think, okay. All right.
No, well, yeah. Actually.